Hello dear students, welcome to the ISRO online platform. For the ISRO series, I am Malakondaiah Gandham, Thermal faculty. I have more than 25 years of experience in the teaching field. Okay. Now in the ISRO, thermal part includes thermodynamics. Thermal part includes thermodynamics, refrigeration and air conditioning, that is called RAC, and IC engines. From the entire thermal part in the ISRO, you can expect minimum 8 questions. Each question carries 1 mark. Minimum 8 marks. Maximum some 12 marks can be expected. It is varying. In 2016, the highest number of questions asked, around 19 marks asked, means 19 questions asked. But generally, from thermal part 8 to 12 questions are giving. Whereas in the RAC part, there is a separate exam for the refrigeration and air conditioning. Around 35 marks can be expected with RAC, refrigeration and air conditioning. So, this is the separate exam conducted by the ISRO only. Okay. Having this introduction, let us start the questions, previous year questions. First question from the refrigeration. It is asked in the year 2016. Look at this question. It is asking like this. The working temperatures in evaporator and condenser coils of a refrigerator are minus 25 degrees centigrade and 30 degrees centigrade respectively. Here, evaporator temperature means the lowest absolute temperature. That lowest absolute temperature given minus 25, but take temperatures always in Kelvin plus 273 to get in Kelvin. Okay na? That is the absolute temperature, lowest absolute temperature. It may be wrong, it might be minus 5, not minus 25. Let me check it, 1 minute, let me check it. నిమిషం లైన్లో ఉండలే, ఇది కొంచెం మిస్టేక్ అయింది, అదే minus 20. ప్రాపర్టీస్ సైకిల్స్ టర్బైన్ తర్వాత Okay, anyhow, based on the given value, it is minus 25 degrees centigrade. Lowest absolute temperature minus 25 plus 273 and highest absolute temperature 30 degrees centigrade. The highest absolute temperature TH equal to 30 degrees centigrade, 30 plus 273. Okay, the COP of the refrigerator is 0.85 times the maximum possible COP. You know, maximum possible COP is the reversed Carnot cycle COP. It is given that actual COP is 0.85 times the maximum possible COP. Let me write that point. Here actual COP is equal to 0.85 times the maximum possible COP. You know, maximum possible COP is depending on only temperature limits 0.85 into reversed Carnot cycle COP, the lowest absolute temperature by highest minus lowest absolute temperature. Substitute here for getting the actual COP. Then for power input of 2 kilowatts, the refrigeration effect produced is, here it is given power input is 2 kilowatts. Power P equal to 2 kilowatts. What is the refrigeration effect? That is the question. As you know, the actual COP equal to actual COP formula already we have written. Actual COP equal to refrigeration effect by power input. Here actual COP already we have written 0.85 times the lowest absolute temperature by highest minus lowest absolute temperature is equal to refrigeration effect dividing by the power input is given 2 kilowatts. Substitute here the temperature limits for getting the refrigeration effect. Okay, so here I got refrigeration effect. Refrigeration effect is around 7.6 kilowatts. That is right. So this may be needed calculator, but no, generally in the ISRO questions are asking such that the solution cannot be found without calculator, but right, we need to do it. So you simplify this value. I calculated, my calculator has shown the right what the 7.6 kilowatts. Try it. It is 7.6 kilowatts. Therefore, option A is absolutely correct. Okay, na? Understood clearly? Problem is simple only, but it is requiring some time for calculation. Similarly, look at the another problem asked for the internal combustion engines. Look at this one. For the same compression ratio, the thermodynamic cycle in the order of decreasing efficiency. What is the order of decreasing thermal efficiency of 3 cycles, namely dual, diesel and Otto? Dear friends, remember the dual cycle is the combined cycle of Otto and diesel cycle. Therefore, believe me, the dual cycle efficiency always in between Otto and diesel or diesel and Otto. That means if you know the relation between the Otto cycle efficiency and diesel cycle efficiency, in between those two you can keep the dual cycle efficiency, because it is the combined cycle of Otto cycle and diesel cycle. Because in the Otto cycle the total heat is supplied at constant volume, whereas for the diesel cycle the total heat is supplied at constant pressure. But in the dual cycle, what is happening? A part of the heat at constant volume, the remaining part of the heat is supplied at constant pressure. That is why the dual cycle is the combined cycle of Otto cycle and diesel cycle. Now anyhow, let us take the efficiency formula for Otto cycle. Otto cycle efficiency 1 minus 1 by compression ratio power gamma minus 1. Okay, next. Diesel cycle efficiency 1 minus 1 by RC compression ratio power gamma minus 1 into rho, that is cut-off ratio, rho power gamma minus 1 by gamma into rho minus 1, gamma into rho minus 1. It can be also written as it can be also written as 1 minus some k by Rc power gamma minus 1, k by Rc power gamma minus 1, where k equal to what? K equal to rho power gamma minus 1 by gamma into rho minus 1. As you know that adiabatic index gamma for air it is 1.4, that is more than 1, and cutoff ratio always greater than 1. Cutoff ratio always greater than 1, right? Remember, believe me, cutoff ratio, the reason why the cutoff ratio more than 1 is cutoff ratio equal to compression ratio by expansion ratio. For diesel cycle, compression ratio is more than expansion ratio, whereas for Otto cycle both compression ratio and expansion ratio both are equal. But for diesel cycle, since compression ratio is more than expansion ratio, cutoff ratio always more than 1, because the cutoff ratio is the ratio between the compression ratio and expansion ratio. Anyhow, you take any value for rho, let it be 1.2, any value you can take it which is more than 1. You substitute here, for getting this k value is more than 1. This k value your calculator will show, this k value will be giving, this k value you are getting more than 1, more than 1. Now look at the diesel cycle efficiency. Diesel cycle efficiency equal to 1 minus k by Rc power gamma minus 1, compression ratio power gamma minus 1. We concluded this k is greater than 1. K is greater than 1. Now compare the greater than 1. Compare these two. Otto cycle efficiency 1 minus 1 by Rc power gamma minus 1, whereas diesel cycle efficiency 1 minus greater than 1 by Rc power gamma minus 1. For the same compression ratio, you know, this quantity, this factor for diesel cycle is more compared to this quantity. 1 minus higher value will have the lower value. From that I can conclude that diesel cycle efficiency less than Otto cycle efficiency for the same compression ratio, right? Including the dual cycle efficiency, diesel cycle efficiency less than dual cycle efficiency less than the Otto cycle efficiency. That is the decreasing order. That means Otto cycle efficiency more than dual cycle efficiency more than diesel cycle efficiency. Look at the options. Decreasing order of efficiency na Otto is more than, dual is more than diesel cycle efficiency. You can select the option D. You should be very careful while you are reading the question. It is not asking for increasing order of efficiency. It is asking to decrease the. It is asking to decide the decreasing order of efficiency. Understood clearly? Yes. Similarly, look at the another problem asked from the internal combustion engines. It is asking like this: 1 kg of carbon monoxide, it is not carbon, it is carbon monoxide, requires how much quantity of oxygen to produce 11 by 7 kg of carbon monoxide gas, right? It is like this. As you know, carbon is reacting with the oxygen to produce the carbon dioxide. Carbon dioxide. It is indication of complete combustion. It is indication of complete combustion. But in our case, carbon monoxide given. Carbon monoxide. As you know, if carbon monoxide is reacting with oxygen to produce the carbon dioxide, let us balance it first. Here it is 2, here it is 2. Yes, now it is chemically balanced. Now let us write the molecular weight on both sides. 2 into carbon molecular weight is 12, oxygen 16, plus oxygen O2 now, O 16, O2 32, gives rise to C2 into CO2, you know it 44. Otherwise I can write like this. C 2 into C 12 plus O2 32. Simplify it. 12 plus 16, 28. 28 into 2, 56. 56 kg of carbon monoxide demands 32 kg of oxygen to produce 32 plus 12, it is 34, 44, 44 into 2, 88. Then 1 kg carbon monoxide requires 32 by 56 kg of O2 for producing 88 by 56 kg of carbon dioxide. It is asking 1 kg mass of carbon monoxide requires how much quantity of oxygen, how many kgs of oxygen, right? Simplify this part. Here it is 8 4 times, 8 7 times. So 4 by, that means 1 kg mass of carbon monoxide is demanding 4 by 7 kg of oxygen to produce. Here also let it be 8 11 times, 11 by 7 kg of carbon dioxide, 11 by 7 kg of carbon dioxide. Then how many kgs of oxygen is required for complete combustion of the carbon monoxide to carbon dioxide? 4 by 7 kg of oxygen. 4 by 7 kg of oxygen. Option A is absolutely correct. Are you following clearly? Yes. Similarly, look at this one. It is also from IC engines, internal combustion engines. Look at this question. It is asking like this. A diesel engine develops a brake power of 4.5 kilowatts. Given brake power equal to 4.5 kilowatts. Its indicated thermal efficiency is 30%. Indicated thermal efficiency given 0.3 and mechanical efficiency equal to 0.85, 85%. Considering the calorific value of the fuel 40,000, calorific value equal to 40000, one more 0, kilojoules per kilogram. The fuel consumption, you are asked to decide what is the amount of fuel consumption. It is in kg per hour given, okay na? Now, as you know, mechanical efficiency formula is what? Brake power by indicated power. From this indicated power equal to brake power by mechanical efficiency. Brake power given 4.5, mechanical efficiency 0.85. 4.5 divided by 0.85, that is indicated power. Then as you know, indicated thermal efficiency equal to indicated power divided by mass of the fuel multiplied by calorific value. Okay. From this mass of the fuel you want, mass of the fuel equal to indicated power by what? Indicated thermal efficiency multiplied by calorific value. Indicated power is 4.5 by 0.85. 4.5 by 0.85 into indicated thermal efficiency. Look at that value, 0.3, 30%, 0.3 multiplied by calorific value given 40,000. Simplify it for getting in kg, kilogram per second. But all our options are given kilogram per hour. To get kilogram per hour, let this is the x value. Multiply this x with the 3600 and simplify it. My calculator has shown, I calculated it, my calculator has shown, right, 1.6 kg per hour. My calculator has shown 1.6 kilogram per hour. That is the answer. Simplify it. Okay. Look at the value, option C. Option C is absolutely correct. Okay na? Lengthy problem, easy only, lengthy problem. Okay na? Shall I take the next one? Yes. Similarly, look at another problem from psychrometry. Look at this value. Look at this question. Try to read the question clearly. It is asked for the ISRO in the year 2011, asking like this: 1 kg of moist air of RH, you know RH means relative humidity. Let me write the given data. RH value equal to 0.7 at 21 degree centigrade is cooled at constant pressure of 1 bar and 5 degree centigrade. That means initial dry bulb temperature is 21 degree centigrade. Otherwise, let me write it clearly. Initial dry bulb temperature dBT1 equal to 21 degree centigrade. 21 degree centigrade. And pressure is given, of course, initial that is called barometric pressure. Barometric pressure equal to 1 bar. Barometric pressure is equal to 1 bar. It is cooled to a dry bulb temperature dBT2 5 degree centigrade. 5 degree centigrade. The vapor pressure at 21 degree centigrade, partial pressure of the saturated water vapor. You know, at dry bulb temperature, the pressure is saturated water vapor pressure, PVS1. Partial pressure of the saturated water vapor corresponding to 21 degree centigrade given 0.025 bar. 0.025 bar. And corresponding to 5 degree centigrade, that is the partial pressure of the saturated water vapor at 5 degree centigrade, 0.0087 bar. 87 bar. The percentage of water vapor that condenses into water at 5 degree centigrade. What is the percentage of the water vapor condensed? That is the question. For that first let us take the percentage of the water vapor condensed is nothing but percentage of change in specific humidity. Okay. You know specific humidity formula. Specific humidity equal to 0.622 into PV by PB minus PV. That is the formula. That is the specific humidity formula. But PV is not given. For that, what you do is, by making use of RH value, you can find the PV. You know RH value equal to what? RH equal to PV by PVS. Partial pressure of the water vapor by partial pressure of the saturated water vapor. Here RH value, let us take this is constant. This is constant. Then PV equal to partial pressure of water vapor equal to RH value into partial pressure of the saturated water vapor. Then partial pressure of the water vapor at the initial state 21 degree centigrade is RH into this is the 1 minute. RH into PVS1. You substitute here for getting the partial pressure of the saturated water vapor. Similarly, partial pressure of the water vapor corresponding to 5 degree centigrade, RH value into PVS2. PVS2. Then specific humidity at state 1 equal to 0.622 into PV1 by PB minus PV1. PV1. Okay. Similarly, specific humidity at state 2 equal to 0.622. This is standard formula. PV2 by barometric pressure minus PV2. PV2. Then change in specific humidity, delta W equal to W minus W2. Percentage change in 1 minute. Percentage change in specific humidity. That percentage change in specific humidity is nothing but the percentage of the water vapor removed from the air equal to that W1 minus W2 divided by W1 into 100. You simplify it for getting what this one. So, my calculator has shown 66%. 66%. Simplify this value. Understood clearly? Are you following clearly? Yes. You are right. You may have doubt that how do you get this particular formula, right? That formula can be obtained like this. Specific humidity general formula is what? Mass of the water vapor divided by mass of the dry air. You know PV equal to mRT. This is the ideal gas equation. From this m equal to PV by RT. Then mass of the water vapor equal to PV VV by RV TV, and mass of the dry air equal to PA VA by RA TA. Okay, substitute here. You know, volume of the dry air and volume of the water vapor both are remaining same. Mass of the water vapor equal to PV, partial pressure of water vapor, VV divided by RV into TV divided by PA VA divided by RA TA. But as you know, the temperature of the water vapor and temperature of the dry air both are remaining same. Volume occupied by the water vapor and volume occupied by the dry air remaining same, because the dry air and water vapor both are homogeneously mixing in the atmospheric air. Then specific humidity equal to partial pressure of water vapor divided by partial pressure of the dry air into the gas constant of the dry air divided by gas constant of the characteristic gas constant of the water vapor. It is partial pressure of the water vapor divided by, as you know, the barometric pressure equal to partial pressure of the dry air plus partial pressure of the water vapor. From this partial pressure of the dry air equal to barometric pressure minus partial pressure of the water vapor. You substitute that, right? Barometric pressure minus partial pressure of the water vapor. Okay. Then here RA, you know, according to Avogadro's law, product of molecular weight and gas constant is the universal gas constant. From this R equal to RU by M. Here it is RU, right? RU, then it can be written like this: RA equal to RU by MA, RV equal to RU by MV. Substitute here. RU cancel. Finally, it is mass of the water, molecular weight of the water vapor by molecular weight of the dry air. Molecular weight of the water vapor 18. Molecular weight of the dry air 28.96. You simplify it, that 18 by 28.96. 18 by 28.96 will give around 0.262. Got that point? Yes. Similarly, look at the another question asking like this: the bypass factor of cooling coil. Bypass factor means what? You know, by the time the air is flowing through a pipe, you may be connecting either cooling coil or heating coil. You cannot say that 100% of the air which is entering to the system is in contact with the heating coil or cooling coil. Some quantity of the air is always trying to escape from the system without contacting the cooling coil. Let us say I am supplying 1 kg mass of air per second. Per second 1 kg mass of air is entering. This 1 kg mass of air fully may not be contacting with the coil. Let us say among the 1 kg, 0.85 kg of air is contacting with the cooling coil in 1 second. The remaining is escaping from the cooling coil without contacting. That quantity of the air which is trying to escape from the system without contacting the coil is called bypass factor, right? That bypass factor cannot be avoided, but you can decrease the bypass factor that is escaping factor, or you can increase the contact factor by connecting the number of extended surfaces called fins with a small gap. Similarly, when the air velocity is more quantity of the air is trying to escape from the system, right, without contact. That therefore, when the air velocity is increasing, the percentage of the air escaping without contacting the coil is going to increase. That means bypass factor increases. That's why air velocity must be low for increasing the contact factor. So anyhow, look at the options. The bypass factor of cooling coil decreases with increase in velocity of the air passing through it, increasing with increase in velocity of the air passing through. Absolutely correct. When the air velocity increases, more quantity of the air is trying to escape without contacting the coil. That means bypass factor is going to increase with increase in velocity. Therefore, you can opt the option B. Understood clearly? Simple question, right? Similarly, look at this one. It is from the properties of pure substances. Look at the options. The critical point and the triple point. You know, this is the critical temperature, critical pressure. Triple point state temperature, triple point state pressure. Don't pronounce as a triple point. Triple point is not a point. Triple point state. Remember, the triple point state looks like a point only with pressure versus temperature coordinate system. Either with TV coordinate system, that is what, temperature versus volume coordinate system, or pressure versus volume coordinate system. Either it is temperature versus volume or pressure versus volume. The triple point state looks like a line, straight line, horizontal line. These are triple point state. Triple point state looks like a horizontal line or straight line with a TV diagram or PV. That's why it is always advisable to call as a triple point state, not triple point. Anyhow, the data is given, critical temperature given, critical pressure given, critical temperature, triple point temperature given, triple point pressure given. Then what you are asked to find? Indicate the phase change that will occur in the following cases. Ice at 0.5 kilopascal is heated. Now you compare the ice pressure with triple point pressure. Here ice pressure is more than triple point pressure. When you heat the ice or when you heat any solid which is below its triple point state, all of a sudden the solid state is directly becoming vapor state without having the observable phase change. That is called sublimation process. Remember that sublimation is happening, right, only below the triple point pressure. Anyhow, for our ice, the pressure is less than the triple point pressure. When the ice is heated at constant pressure, isobarically means constant pressure, definitely the solid state of the ice is becoming vapor state. That is marked as AB. That is called sublimation. That means the first case, right, sublimation is happening along the AB. Along the AB, only one option is available. Look at the other one. Water vapor at 400 degrees centigrade. Look at this 400 degrees centigrade, which is above the triple point temperature. It is above the critical point temperature. Sorry. The given temperature of the steam, water vapor, is above the critical temperature. Then what is happening? The gas is available above the critical point. Right? When that vapor is compressed, isothermally, what is happening? When that vapor is compressed isothermally, right? Isothermally, the pressure is going to increase from C to D. C to D along the CD. Direction is very, very important. C to D along the CD. So the compression isothermally happening along with the CD. The sublimation along the AB is happening because the pressure of the ice is below the triple point pressure. Therefore, option A is absolutely correct. The problem is looking complicated but very, very easy. Okay, understood clearly? Yes. Similarly, look at the other one, also from properties of pure substances. Asking like this, the positive value of Joule-Thomson coefficient of a fluid means Joule-Thomson coefficient. As you know, the Joule-Thomson coefficient mu Jt equal to Joule-Thomson coefficient is the slope of isenthalpic curve with temperature versus pressure coordinate system. Take the temperature versus, not pressure versus temperature. Here temperature is on y axis, right? Temperature versus pressure axis. 1 minute. TP diagram, temperature versus pressure. Here Joule-Thomson coefficient mu Jt equal to dou T by dou P at constant enthalpy. As you know, Joule-Thomson process is also called isenthalpic process or throttling process. It is mainly for dropping the pressure. Pressure is keeping on dropping. Pressure is keeping on dropping during the entire Joule-Thomson expansion process or throttling process. That means 1 to 2 is the representation of throttling process. Actually, throttling process is the irreversible process. Irreversible process should be marked with the broken line only. That means indirectly this 1 to 2 line or curve must be marked with a broken line only, because thermodynamic sense is for reversible process such that the irreversible process should be marked with a broken line. Anyhow, this is a representation of throttling process. Now look at the first half process. 1 to, let it be A, 1 to A, right? In this process, though the pressure is dropping, here dou P, pressure is dropping means dou P, change in pressure is negative. But look at the temperature, temperature is going to increase, change in temperature is positive. Then what is the Joule-Thomson coefficient for the 1 to A process? For the 1 to A, look at the mu Jt. Let me write. You should be very careful while we are discussing in the limited space. Joule-Thomson coefficient mu Jt equal to dou T by dou P at constant enthalpy. Here dou T positive, dou P negative. Joule-Thomson coefficient is negative. Generally temperature increases in thermodynamics by warming process. Therefore, I can say that first half process is warming process. Because temperature increases. Look at the next half process, that is A to 2. That is from A to 2. Right, for the A to 2, temperature is dropping. That means dou T negative. Pressure is also dropping. Dou P negative. Since dou T and dou P both are negative, Joule-Thomson coefficient mu Jt equal to dou T by dou P at constant enthalpy. Since numerator part is negative, denominator negative, Joule-Thomson coefficient is positive. But in this process, since temperature is dropping, thermodynamically temperature is dropping by cooling process. Therefore, Joule-Thomson coefficient is positive for the cooling process where the temperature is going to drop. From that, the moral is the Joule-Thomson expansion, that is throttling process, can be possible by the combined effect of warming process and cooling process. Combined effect of warming and cooling only can maintain the constant enthalpy in the throttling process. Anyhow, look at the question. A positive value of Joule-Thomson coefficient means what? Temperature drop during the, look at this one, look 1 minute. A positive value of Joule-Thomson coefficient, positive value, here dou T should be negative, correct? Temperature drop during the throttling, option A is correct. Right? Joule-Thomson coefficient negative for a warming process, positive for the cooling process. Cooling means temperature is dropping, already we have discussed. The Joule-Thomson coefficient is positive when the temperature is dropping, but pressure is keeping on dropping in the entire throttling process. Are you following? Yes. So anyhow, for this you can select the option A. Okay. Similarly, look at this one. Is it correct? Temperature drops. Yes. Look at the next one. It is from availability. The maximum theoretical work obtainable when a system interacts to equilibrium with the reference environment, means surroundings, is called availability, is also called exergy. The maximum work what we can expect from a system when it is operating reversibly, when it is interacting with the surroundings isothermally, is called what? Exergy or availability. Therefore, option C, very simple question. Okay na? Yes. Similarly, look at the other one. Rankine cycle problem. Look at this one, Rankine cycle. Asking like this, air is accelerated isentropically, means reversible adiabatically, from 100 meter per second. Look at the V1, initial velocity V1 equal to 100 meter per second. It is increased to a velocity, let it be V2, V2 equal to 300 meter per second in a nozzle. If the temperature at the inlet is, T1 equal to 127, better to convert it to Kelvin plus 273. What is the value of 127 plus 273? It is 400 Kelvin. 400 Kelvin. Then the inlet Mach number, you are asked to decide what is the Mach number. What is the Mach number formula? Mach number equal to flow velocity by sound velocity. Flow velocity by sound velocity. Since it is asking Mach number at inlet, V1 by A. A is called sound velocity. Okay. What is the sound velocity formula? Sound velocity. Look at the sound velocity. Sound velocity is also called acoustic velocity. A equal to root over gamma RT. Gamma RT. Make sure that R should be in joules per kg Kelvin. Look at the gamma value given. Gamma value. Gamma, where gamma given is 1.4. R value, it is given 287 joules per kg. 1.4 into 1.4 into 2, it should be in joules per kg Kelvin, right? Multiplied by temperature, we got in 4. You simplify it. Simplify this value, right? This is the what this sound velocity. Sound velocity. Now this this what V1 equal to what? V1 equal to 100. V1 equal to 100. Dividing by sound velocity, root over 1.4 into 287 into 400. Simplify it for getting the answer. My calculator has shown what 0.249. 0.249. 0.24, absolutely correct. 0.24. Simplify it. Okay, for this calculator it may be required. So this is the what simple question. Understood clearly? Yes. Similarly, your answer is 0.249. Okay, na? Similarly, look at this one. From the first law of thermodynamics, look at this one. 1/100th of a kilogram of air means mass of the air given. How much? 1 by 100 kilograms. 1 by 100 kilograms means 0.01 kilograms. Yes. Is compressed in a piston cylinder device at an instant of time t given, of course, t given, directly given 400 Kelvin. You need not to worry. The rate at which work is being done on the air. Work done on the air, negative. Work done by the air is positive. Okay. So indirectly dW by dt, rate of change of work is, alright, 8.165 kilowatts. It should be written with a negative sign because work done on the air. Okay. And heat is being removed. Heat is removed, not heat supplied. Heat supplied is taken as positive. Thermodynamically, heat removed is taken as positive. Heat removed is taken as negative. Heat removed at the rate of, that means indirectly, dQ by dt. dQ by dt, how much it is given? 1.0 kilowatts. But is it positive or negative? Removed. Heat removed is taken as negative. Negative. Okay. Then the rate of temperature rise will be, what is the rate of temperature? Means the temperature rise in 1 second. That is the meaning of rate of temperature rise. Okay. For that, you need to take the steady flow energy equation. As you know, Q equal to W plus dE. This is the non-flow energy equation. Remember, this non-flow energy equation can be applicable for both reversible process and irreversible process. If the system is closed system, because that is the non-flow energy equation, that is for non-flow system, means closed system. Then it can be also written as dq by dt. Here it is better to write d small t. Time, no? Rate means time, better write small t, because we are marking capital T for temperature, small t for time. Okay. dq by dt equal to dw by dt plus dE by dt. dE by dt. dq by dt, look at the dq by dt, minus 1, write that value, is equal to dw by dt minus 8.165 minus 8.165 is equal to dE by dt. You bring this one to the other side, it is giving 7.165, because this is becoming positive. If you bring it to other side, that is equal to dE by dt. Then dE, here you got dE general formula what? dE general formula m into Cv into dt, according to Joule's statement. So dE by dt I can write is m into Cv into dt by dt, capital T for temperature, small t for time. That d capital T by d small t, rate of rise in temperature, it is equal to we got 7.165. It is in kilowatts, 165 kilowatts. Then the Cv should be in kilojoules per kg Kelvin. Cv equal to 0.718 or 717. So mass is 0.01 into 0.718 into d capital T by d small t equal to 7.165. From this you can decide the rate of rise in temperature. My calculator has shown around 1000 Kelvin, that is the temperature rise in 1 second, Kelvin per second. Look at the options. Option C is absolutely correct. Okay, understood clearly? Very simple. Similarly, look at the other problem, also from first law of thermodynamics, given like this. The inlet and outlet conditions of steam for adiabatic steam turbine. Adiabatic means here heat transfer is 0. There is no heat transfer, either from system to surroundings or surroundings to system, are as indicated in the figure. The notations are as usual followed. If the mass rate of steam is 20 kg per second, the power output of the turbine, mass flow rate of the steam given, mass flow rate of the steam m dot equal 20 kilograms in 1 second. Velocity given, elevation given, enthalpy given, of course pressure also given. The same quantities are given at outlet. Then you are asked to decide power. For that, better take the steady flow energy equation, because the steam turbine is coming under steady flow device. For any steady flow device like gas turbine or Pelton wheel, like water turbine or steam turbine or centrifugal compressor, axial flow compressor, these are all the steady flow devices. For all these steady flow devices, you can take the steady flow energy equation. Similarly, throttling process also steady flow process. That enthalpy constant we are deciding by making use of a steady flow energy equation with the throttling process. Okay. Anyhow, the steady flow energy equation is mass flow rate of the steam, otherwise 1 minute. First let me write per kg, V1 square by 2 plus GZ1 plus H1, this is per kg into mass flow rate, plus Q dot, it should be outside, is equal to per kg it is V2 square by 2 plus GZ2 plus H2, this is per kg, multiply with mass flow rate of the steam plus power output. Anyhow, for this particular case, adiabatic condition given Q equal to 0. Here I am going to write like this, m dot into V1 square by 2000. The reason why I wrote 2000, is H1 H2 given in kilojoules per kg. That's why you have to take the kinetic energy in kilojoules per kg. Similarly, the potential energy also GZ1 by 1000. Then only you will get the your calculator or you will get the correct answer plus H1. H1 you need to write the dividing by 1000 because H1 itself is given in kilojoules per kg. It is equal to mass flow rate that is given 20 kg per second into V2 square by 2000 plus GZ2 dividing by 1000. Should be very careful with the units, right? Plus H2, it is given in kilojoules per kg plus power. You decide the power from this formula. Decide it. My calculator has given 12.157 kilowatts. This is the power. I got it, 12.157. Okay, look at this one, 12.157 there, 12.94 is there, option A can be selected. Can a simple problem. Problem is looking lengthy but very easy. Just should know the steady flow energy equation. Okay. Similarly, look at the other problem from the gas turbine. Look at the problem. Asking like this. The work ratio of gas turbine is a function of. For deciding the answer, you should know the definition for or what is the meaning of work ratio, right? Here work ratio is what? Work ratio equal to ratio between the net work and turbine work. Net work and turbine work. Net work again what? Net work means turbine work minus compression work dividing by turbine work. It is equal to 1 minus compression work by turbine work. Of course, this ratio, the compression work dividing by turbine, that quantity is called back work ratio. Anyhow, this is the work ratio, right? It is equal to, compression work general formula for gas turbines Cp into T2 minus T1. Turbine work formula Cp into T3 minus T4 by marking the TS diagram, simple TS diagram. The gas turbine power plant works on the Brayton cycle. The Brayton cycle has only two pressure limits. TS diagram. Pressure before compression, let it be P1. Pressure after compression, P2. Remember, though the slope of the each constant pressure line is remaining same, the constant pressure lines in the TS diagram for the gas turbine power plant are diverging from left to right. Okay. Now 1 to 2 is the compression process. Simple diagram. 1 to 2 isentropic compression, where the temperature is increasing from T1 to T2. Okay. Followed by 2 to 3 heat addition process at constant pressure, followed by 3 to 4 isentropic expansion, followed by constant pressure heat rejection process. For the 1 to 2 process, since it is reverse adiabatic process where entropy constant, you can write that T2 by T1 is equal to P2 by P1 power gamma minus 1 by gamma. This I can write as pressure ratio, RP, pressure ratio power gamma minus 1 by gamma. Okay. Now, for the 3 to 4, look at the 3 to 4. For the 3 to 4, where entropy constant, temperature limits for 3 to 4, before expansion temperature is T3, after expansion T4. Temperatures are changing for the same pressure ratio only or pressure limits only. I can write that T3 by T4 equal to P2 by P1. The same value I can write it, RP power gamma minus 1 by gamma. Okay. Now let us substitute here 1 minus compression work. Compression work is Cp T2 minus T1 dividing by turbine work is Cp T3 minus T4. Cp is cancelling, 1 minus. Let me write the T1 outside from the numerator because that is the lowest temperature. It is becoming T2 by T1 minus 1 dividing by T3 outside from the denominator. It is becoming T4 1 minus 1 minute. 1 minus T4 by T3. T4 by T3. Okay. Now it can be also written as, let us go back to this one. Okay. The work ratio equal to what you got is 1 minus 1 minute. T1 by T3. T1 by T3 into this T2 by T1. Look at this T2 by T1. T2 by T1 equal Rp power gamma minus 1 by gamma. Rp power gamma minus 1 by gamma minus 1 by 1 minus this 1 minus, since T3 by T4 is Rp power gamma minus 1 by gamma, T4 by T3 1 by Rp power gamma minus 1. It is like this, 1 minus 1 by Rp power gamma minus 1 by gamma. It is equal to 1 minus T1 by T3. Simplify it. Rp power gamma minus 1 by gamma minus 1 by Rp power gamma minus 1 by gamma minus 1 by Rp power gamma minus 1 by gamma. This part is cancelled. Finally, 1 minus T1 by T3 into Rp power gamma minus 1 by gamma. That is the formula for getting the work ratio. Now, the work ratio of the gas turbine is a function of temperature ratio, that is T1 by T3, and pressure ratio Rp, right. So, both look at this one, the work ratio is depending on temperature ratio and pressure ratio, right. So, option A is absolutely correct. Okay. Similarly, look at this one, right, air cycle. For the same values of peak pressure, means maximum pressure and maximum temperature and heat rejection, the correct order of the efficiency. Remember, for the same maximum pressure and maximum temperature and heat rejection, remember diesel cycle efficiency of the diesel cycle is more than efficiency of the dual cycle, more than efficiency of the Otto cycle. Remember, under maximum pressure condition, diesel cycle efficiency is more than Otto cycle efficiency. Okay. Whereas for the same compression ratio and heat input, Otto cycle efficiency more than diesel cycle. Whereas this fellow dual cycle efficiency always in between Otto and diesel or diesel and Otto. If therefore, this is asking order efficiency of diesel cycle is more than Otto cycle efficiency more than dual cycle efficiency. Okay. Similarly, look at the another question for the air cycles. A cycle consisting of one constant pressure, one constant volume and two isentropic, that is called diesel cycle. The Otto cycle is having two isentropic process and two isochoric process, whereas diesel cycle, for diesel cycle, heat addition at constant pressure, heat rejection at constant volume, but compression and expansion isentropic. Anyhow, option D, diesel cycle is having one constant volume process, one constant pressure process and two isentropic process. Similarly, right, work and heat, okay, you just practice this question, right, practice this question. So, with this, this also you try this question, this is also important question, right. With this, dear friends, I am concluding because of some lack of time. I have given 2 questions, right, homework. Okay, I hope all of you clearly understood or not. Okay, thank you. All the best. God bless you.